Am I audible to everybody?
Yes, ma'am.
Okay. So last time we saw the cellulose acetate paper. Okay, paper electrophoresis. Electrophoresis and chromatography. These are the two techniques which are used for separation, for studying the purified protein. Both of them have their advantages. So electrophoresis can be done on a smaller scale in the laboratory. Column chromatography also can be minimized, can be done on a smaller scale these days, and both of them have their own advantages. So we are now studying the different ways or different techniques of how do you go about when you have a crude protein extract with you. Now this could be a bacterial protein, a fungal protein, or it could be anything. If you are into healthcare and if you are actually working with blood and serum samples, then in that case also you can determine what is present actually in the sample. You can also do the electrophoresis technique to find out to study that particular component that you are actually looking to purify and to separate from the others. Because when you are given a mixture, it is very difficult to study an analyte of your interest from the mixture. So the first thing you have to do is separate the analyte, and separation will, when you want to separate, of course, chromatography and electrophoresis are the two techniques that can be used. Starch gel electrophoresis is also one of the types. It is preferred, but again, it is less preferred because there are making the gel, making a starch slab and all that again requires a lot of technical skills. So starch gels are prepared. You have a starch powder. Basically, the starch powder used here is potato starch. Okay, I would like you all to note down things, because for the multiple choice questions that are going to be there as a part of your mid-semester exams, all these things also may come, even if they are not on the slide, but I am telling you all. So please make sure that you all are noting things down. Okay, these are the minute details. So when we talk about the, just a minute, I'll connect my pen tab. Starch gel, you have a potato starch and you have it in a powder form. Now that powder form has to be converted into a gel form. So basically what you do is you add the starch powder to a medium. Now that medium can be a buffer medium. So the powder you take, say if you take a powder, weigh out some powder, and if you add buffer, because you will be running a protein sample or you'll be running a biomolecule, and we know that biomolecules are very specific about pHs. So you make a mixture. That mixture is heated, and that mixture is heated. After heating, starch, basically a starch solution is a colloidal solution. It's not a true suspension. It is not a clear suspension. So you will see it is cloudy. Okay, and after you heat it, it will become a colloidal solution, but it will look like a homogeneous colloid solution, if you understand what I mean. So it'll look uniform. It'll get uniformly mixed with water. Starch is insoluble in water, but it gelatinizes, and then when you cool it, you will see that a thick slab kind of a thing is formed. So that is what is starch gel now. So starch gels are prepared by heating and then cooling a solution of partially hydrolyzed starch in an appropriate buffer. And the separation is accomplished due to the differences in charge. When we are working with proteins, proteins do carry charge. So if you're talking about, say, this protein here, it's a folded structure. It's three-dimensional. Okay, now what will happen? What is protein made up of? Please now type down the answers in the chat box. What is protein made up of? What are the basic components of proteins? Is it made up of glucose? Is it made up of amino acids? Is it made up of lipids? What is protein made up of? Yes, thank you very much. It is made up of amino acids. So you will see that there will be a lot of interaction. So if these are the amino acids, the beads, okay, these are the beads. I'm using green color, which means that they're of the same type, but I want to show that they will not be of the same type. There will be different amino acids which will be making different, which will be involved in the protein. Okay, so now what is going to happen is there will be some interaction between the amino acids. Okay, there will be interaction and there will be bond formations. So hydrogen hydrogen bond, covalent bond, amido link, so they will form a peptide bond. Okay, the peptide bond basically. I think I told you all that till today, whatever we are going to study is going to be the syllabus. Last time, Juhi, were you there last time in the class? I told you, like, till today's lecture. Okay, has everybody understood? Can you all please say yes so that I get a confirmation that everybody has understood?
Yes, ma'am.
Okay, everybody. Akshata, you are a CR, so I am just assuming that you are going to circulate this message once again to all of them that yes, whatever we are doing till today is going to be a part of the mid-semester. The question paper has already been made based on that. Okay, now there are going to be these interactions, amino acid interactions, and these interactions are going to hold the protein in a particular structure. It will fold the protein into a particular structure. Now what will happen again is that these amino acids also carry charge. Okay, all the amino acids carry charge. Some carry positive charge, some carry negative charge. It means that the protein also has a charge. So the protein also has a charge and it also has mass. So again, when we are doing a starch gel electrophoresis, we will definitely consider the charge to mass ratio here. Okay, now this charge could be positive, this charge could be negative, it could be highly positive, okay, or it could be also highly negative, because this protein is made up of positive and negative amino acids, right? Positively charged negative acid and negatively charged amino acid. So depending upon which charges are more, the protein will bear that charge. So the separation is accomplished due to the differences in the charge as well as size of the molecules. Because when you're talking about making a slab or making a gel, there is going to be a sieving effect. So again, if you look at a slab, you look at a gel, you will see that it's a very jelly-like thing, soft, smooth, and everything. But when you look at under, say, a detailed structure, if you look under a microscope, you will see that there are meshes like this inside the gel. And when you are loading your protein onto this gel, when you are running a sample, for example, this is one protein. I've given you a mixture of proteins and you're going to run it now. These are the small, big molecules mixture. So when you apply the electric current, they will migrate. And when they will migrate, depending upon the size, they will migrate. They can, depending upon the molecular size, their weight, their shape, they will migrate through these network, or they will migrate through these, we can call them as sieves that are formed. So it gives a sieving effect. Okay, it's also called as molecular sieving. So depending on the pore size of your gel, depending upon the pore size of your medium, the molecular sieving can happen and the separation of the proteins can happen. Okay, so this is about starch gel. If you look at the chemistry, then you know that starch is what? Starch is a monosaccharide or a polysaccharide. What is starch? A monosaccharide or a polysaccharide? It is a polysaccharide made up of, which is a basic unit of starch. What is the basic unit of starch? If it is a polysaccharide, then glucose. Yes, correct. Glucose is the basic unit. So you'll see that there are so many glucose molecules linked together and they form starch. It is a polysaccharide. And the starch that we are going to use is potato starch. You can take 10 to 12% of starch powder and you can add buffer to it, heat it, make sure that you are not having clumps into it, because yeah, you need to be very careful that there are no clumps, there are no air bubbles trapped into the gel while making it. It should be a very, very homogeneous, uniform mixture. Okay, it will look whitish, bluish, cloudy thing. It is not going to be clear. It is not going to be clear as water, your whatever homogeneous support matrix that you're going to make. And then this mix can be poured into a mold of whatever shape. It can be a square, it can be a big rectangle, depending upon how many samples you want to run. And it is also used in the analysis of protein and isoenzyme. Now today we will see the another, we discussed about starch gel electrophoresis, but now we are going to study the two routine techniques that are used in a protein lab, in a molecular biology lab, and which is Agarose gel electrophoresis and polyacrylamide gel electrophoresis. As we have seen that gel electrophoresis is migration of biomolecules, migration of nucleic acid, migration of proteins under the influence of an electric field. So electric field is very, very important. So what does this electric field do? Or what happens when the electric field is applied? When the electric field is applied, again, the biomolecules will carry charge. They will have certain mass. They will have a shape, particular shape. Not all of them are going to be of the same shape. And whatever gel you are going to make, whatever matrix you have casted, I would use the word casted. Okay, that is the word that is used in the laboratories. That cast a gel. I casted a gel. So when you cast a gel, now that gel matrix is going to contain small pores. Something like when we saw what is size exclusion chromatography. If you can relate that to this, the approach is very similar. So the pore size is going to decide that which molecule is going to migrate faster, which molecule will take time along. So one of the influencing factors is the pore size. The other factors are definitely the molecular mass, the molecular weight, the shape, the charge, all of these factors. So the molecules travel through the pores. They have to travel through the pores in the gel at a speed that is inversely related to their length. More the length, less will be the speed. Lesser the length, higher will be the speed. Okay, it is inversely proportional. So this means that when we are talking about agarose gel, okay, agarose gel is commonly used, and I'm sure you will also probably make an agarose gel or cast an agarose gel during your one of the practicals. So agarose gel is very routinely used for DNA fragment isolation, or to after the PCR is done, you have to analyze your PCR sample. So then agarose gel is one of the very commonly used techniques. So DNA molecule will travel greater distance through the gel as compared to the larger DNA. So see, when you have a mixture and that mixture is having different fragments of DNA, so the sizes may vary. Okay, one could be very small, one could be medium size, one could be a large fragment of DNA. So the sizes of the DNA fragment will vary. And when you load such a mix of sample in the agarose gel, and when you apply the electric field, the migration is going to determine who's going to dominate or who's going to determine the migration. It is the fragment size. So longer the fragment size or larger the fragment size, it will take less time. It will take more time to end the journey. And smaller the DNA molecule, smaller the fragment size, it will be so that's what it is, inversely proportional. So smaller will travel a greater distance, and greater will travel the greater the DNA, it will take more time. It will be very, very slow. Okay, so this is how we are going to look at how the agarose gel is made. Now, agarose gel is basically agar, which is treated and from which sulfate is removed, and you get an agarose. It's a powder. It's like a very tiny granular powder, dry powder that you get commercially. It is available commercially. You weigh the gel, you weigh the agarose. Okay, again, it is weight by volume. So you can make 0.3% gel, you can make 0.6% gel, you can make 0.8% gel. So you can make various percentages depending upon the fragment of DNA that you want to see or you want to isolate. Okay, so when you do this, the first step you involve is preparation of gel. You have to weigh the agarose powder, add it to the beaker, add your buffer to it. Again, buffer is important. So all the preparations that we are going to do, column chromatography, gel electrophoresis, whether it is nucleic acid gel electrophoresis or whether it is protein gel electrophoresis, buffer is very, very important. So mix your agarose with buffer, put it in the microwave, boil it in the microwave. So how long are you going to boil? Are you going to boil it for 10 minutes? No, you have to keep watching. You must make sure that the agarose has completely dissolved in the buffer, and it gives you a clear, but it will give you a viscous mix now. So the buffer is not viscous, but after the agarose is becomes molten because of the microwave heat, the whole entire mix is going to be now viscous. To this, you have to allow it to cool down a bit. It shouldn't be very, very hot. Okay, you have to allow it to cool down a bit. So cool the mixture to about 60 to 65 degrees as mentioned here. You should be, then what do you do is you have to add ethidium bromide, okay, to the mix, and then stir it gently. You do not want air bubbles into it, and then you pour it into a mold. Now this mold is sometimes acrylic, okay, it is made up of acrylic base, and then you will have to pour it into a mold. After you pour it into the mold, then you have to insert something which is called as a comb, or it can be said as a comb. Now this comb is actually just like the comb that we use. Have you all done any of your experiments which involves DNA electrophoresis? Have you all seen this unit in the lab?
No, ma'am.
No, you have not. Okay. So you insert the comb. Now it's a jelly-like thing which is still at a warm temperature. Allow it to cool. Allow it to cool down at room temperature. It solidifies. But it is still soft because it is a jelly-like thing, but it solidifies. You remove the comb slowly. When you remove the comb slowly, you will see that these kind of depressions are formed, okay? Because these teeth of the comb lead to formation of such depressions, and they are called as wells. So now these are the wells that are formed, and in this well you are going to load your sample. Can you see this part where you are using a micropipette and you are loading your sample? So these are the samples A, B, and C that you are going to load. And when you load the sample, you're going to apply electric field and you're going to run the sample. So running of an agarose gel could somewhere be from 60 to 90 minutes. Okay, so this is how you you prepare a gel. So first step is preparation of gel, allowing it to solidify, and then when you have poured the molten gel, you have already inserted the comb. When it solidifies, you have to remove the comb. The wells will be formed, and this is the place where you're going to load the sample. Now, you have to also apply tapes on both the ends, because no, we are going to see a video and you will see that this end, this particular end and the end behind the comb, they're open. Can you see that now there is no tape here and there is no tape here? So here, if you were seeing earlier, yeah, see, there is a white tape. Can you see that difference now? There is a tape here. Okay, so there is a tape on this end and there is a tape on that end. It's a rectangular slab. So why do you put a tape? Simply because you want to contain the agarose in this particular mold. If you don't put a tape, the agarose will flow out. Okay, so tape it from both the sides. After the formation of the gel, after the wells are properly formed, remove the tapes. Now it has solidified, it is not going to flow out, but it is still slippery, it can slip out. So you have to handle it carefully. And then you remove the tape and then you load your sample and run it under the electric field. If you do not remove the tape is of course an insulator. It is a bad conductor of electricity. It will not allow the electricity to flow, the current to flow from one end to the other end. And we want that. We want the electric current to flow, because this is based on, the separation is going to be based on the charge. So charge and the fragment size. Okay, what is the charge on DNA? What is the charge on DNA? You can write it in the chat box. Yes. What is the charge on DNA?
Negative.
Negative. So where will it travel to?
Positive.
Positive. So which is the positive terminal of which is the positive terminal known as
Cathode.
anode or cathode?
Anode.
Anode. The positive terminal is known as anode. So the DNA is negatively charged. It will move towards the positive electrode. Okay. So where the wells are going to be, the wells where you are going to load your sample, which side of the terminal it is going to be? Negative, say positive. DNA is going to go from negative to positive. So where will you keep the wells where you're going to load the sample? Which terminal? Cathode terminal. You're going to keep the wells on the cathode terminal, and then you're going to load it and you're going to apply the electric field. So DNA being negatively charged will travel towards the anode. Now, do you also observe that these samples look blue in color? Okay. So when you extract DNA, is the DNA colored? From any source you're going to extract, say leaf, flower, seed, human cells, cheek cells, whichever cells. Is the DNA colored? It is not colored. Okay. Now such a DNA sample, if you load into the well and if it migrates, will you be able to know that till where have you traveled? Where has the gel traveled? So I will apply the electric current and the fragments will start to move, but they are colorless. Okay. Look, so imagine that you are trying to see microorganisms under the microscope, but without staining. Will you be able to see the microorganisms under the microscope without staining? You will not. Okay, because you must have that color which is reflected, and that is what you see under the microscope. And these organisms being colorless, you must add stain or you must add dye to it. Similarly, DNA is also colorless. Whatever extraction protocol you follow, that extraction protocol will have alcohol into it, and isopropyl alcohol is used in the extraction of DNA, which is colorless. So whatever sample you're going to get, so you're going to precipitate the DNA, then suspend it into a buffer. That buffer is also going to be colorless. Everything is colorless, but still you have the material inside. Now to track the material, where it is going, which direction it is going, has it reached till here? Has my DNA reached till here on running, or has it overflowed? Has it come down? So if I don't keep a track, if I don't have colored system to track the journey of the DNA, it will just flow down into the buffer again. So that's why you must have a dye. This blue color is because your DNA, your sample mix is being added with bromophenol blue. Okay, the tracking dye or the loading dye is bromophenol blue. It's a mixture of bromophenol blue and glycerol. So bromophenol blue to samajh mein aata hai. Why is it used? Is because it is helping you to track the run of the DNA. But why glycerol? Because glycerol is having weight. Okay, the DNA sample or another nucleic acid sample, RNA sample, whatever sample you are going to load will not have weight. And as soon as you put it in the well, it might just come out of the well. Okay, and it will just spread into the buffer. So that is of no use. Now your sample should sit inside the well. So to make it sit inside the well, you must increase the density, the weight of the sample, the density of the sample, the molecular mass, the weight of the sample should be heavy. Okay, so that it will settle down. And when you add glycerol to it, it will stick inside the well. It will not ooze out of the well. And that's how your sample is now ready to run. So that's where you will be able to now apply the electric field. Okay. And after the electric field is applied, after the run is over, you remove it. You then keep it on a UV transilluminator. This is called as a UV transilluminator. This is like a, inside there is a UV bulb or UV light. Okay, the surface on top is black color thing, which is a black glass. Okay, and the UV, once you put on the instrument, the UV light is on, and you keep your gel, you slide your gel on this, you cover the lid. Covering the lid is very important because you're working with UV. You should not be exposed, your eyes, your hands should not be exposed to the UV light. So you always cover the machine, or if you don't have a cover, then you have helmets, protective helmets to wear, which will not allow the exposure of eyes. There are some transilluminators which are like a box. You have to open the lid, keep your gel, cover the box, and there's only a small window sort of a thing, which is again covered, from where you can peep and you can see the gel. After you put on the UV light, you will see the bands like this. Now, do you see that these bands are glowing? These bands are fluorescent. Okay, why? Because if you remember, you added ethidium bromide in the beginning. So ethidium bromide is carcinogenic. It has to be handled carefully. Ethidium bromide is intercalating agent. It will go and sit in between the DNA, in between the bases, actually, the purine bases, pyrimidine bases. It is an intercalating agent. And on falling of UV light on ethidium bromide, it glows. Okay, so that is how this, without staining the DNA gel, without actual adding any dye from externally after the gel is over, because of the addition of ethidium bromide, you can see these bands like this based on the UV transilluminator. Now, there are some commercially available substitutes for ethidium bromide, which also glow and which are not carcinogenic. Okay, so ethidium bromide is now removed. Many good labs don't use ethidium bromide because of the harmful nature of it. So it's a less expensive technique, though Agarose is abundantly available with a lot of suppliers. It does cost, but it is comparatively less expensive. It is a good separation technique. Agarose is a sulfate-free fraction of agar, and the gel run is about 90 minutes. Okay. Now, this was about how you run the gel, how you see the gel, how you find out what are there. So this is a ladder. This is called as a ladder. This ladder is, so the length of the fragment is kilobases. So this is a ladder which will tell you these are different kilobases. These are different sizes of DNA. Okay, and this is your standard. This is your standard with which you are going to compare your samples. So this band is somewhere between this band and this band. So you can say that now my band corresponds to this much kb. Okay, or if you get an exact band at this place, then you will know that this is the size, or this is the fragment size of the DNA that I am looking at. So this is your standard and these are your samples. You look at a Agarose gel electrophoresis unit, you will find all these components. A power pack, always there, always important. Whether it is an Agarose gel electrophoresis, whether it is a protein gel electrophoresis, power pack is the important thing. Why? Because it is the one which is going to which is responsible for the current electric field. So one of the component is power pack. Then you have this whole unit. You will see that there are certain depression kind of a thing. So again, these can be wells, and you add buffer into this. Okay, this middle platform is where you keep the gel. Okay, so and then there is a lid, and when you cover the lid, you will see that on the lid you have the connections. They are the electrodes actually. So the black is the cathode, this is the positive electrode, which is anode, which is the red one. And when you assemble the whole unit and you connect this part to the power plug, the current flows through the system. Okay, so I have a video here. Am I audible to everybody clearly, or is my voice breaking? Am I audible?
Yes, ma'am.
Okay, good. So power pack, electrophoresis unit. Okay, these are the two important things that you will also see in protein gel electrophoresis.
In this video, you will learn how to cast an Agarose gel. Start by taping both ends of a gel.
So this is how the unit, sorry, not the mold looks. Okay.
Start by taping both ends of the cast.
Yeah, this is how the mold looks, and these are the combs. So based on the number of samples, you decide what size of platform or the mold you're going to use, and how many number of combs. So if I have 5 to 6 samples or 8 samples, so this is 8 wells. If you count 1, 2, 3, 4, 5, 6, 7, 8. So if you use this comb, you're going to get 8 wells, and one of this is going to be a standard. One well is always reserved for standard. You never run a gel without loading a standard, okay? Because if you think I have already 8 samples now, and if I run a ladder along with it, then I will waste one well. So why not just run all the 8 samples together? But that is of no use. You always have to load a ladder. So ladder plus 7 samples can go into this.
Start by taping both ends of a gel tray with laboratory or painter's tape, making sure to securely seal the edges of the tray. Press down firmly along each edge of the tape to ensure that there are no leaks. Repeat this procedure with the other side of the gel tray, again making certain that each edge has been firmly sealed.
Yeah, so if you don't seal it, obviously whenever you're going to pour the molten mixture, it'll all come out from both the sides. So you need to seal the gel from both the side using these tapes.
Next, place the comb into the comb guides on the gel tray. If you plan to run DNA samples, the comb should be placed at one end of the gel tray. Place the tray with comb on a flat and level surface. Before pouring the molten agarose, make certain that it has cooled to 55 degrees Celsius. Pour the agarose into the gel tray until the agarose comes to within 2 to 4 millimeters of the top of the teeth of the comb.
Yeah, so when you're going to pour the gel, you must make sure that you're not going to pour it till here, okay? Till like this. No, because if you do that, you will not get any wells. You will get just one common, a long stretch of gap, like a, not like a trench. You will not get these wells. So make sure that you're only pouring till this mark. So about just below 1 or 2 millimeters below the end of this comb. And then you will get different wells.
Of the top of the teeth of the comb. When the gel is cool and opaque, remove the comb by pulling it gently straight up and out of the wells. You should be able to see that each well is well formed. If the comb is removed before the gel is set, the wells will collapse.
Yeah, so you have to allow the gel to solidify and then you remove it. If you do not allow the gel to solidify and try to remove the comb, then the gel is going to crack. The wells are going to crack and they will mix into each other. So then you will not be able to load samples properly. They will mix. After loading, the samples are going to be mixed. Also make sure that you are not going to allow the gel to solidify for 1 hour, 2 hours, and then you remove the comb. That's because then it will be too hard to remove. So even that jerk will probably crack the gel. So in such a case, the best thing to do is when you see that the gel has solidified, first pour a little thin layer of buffer. Pour a thin layer of buffer over the gel when the combs are still in. Okay, after it solidifies, after the comb is ready to be removed, pour a thin layer of buffer and then remove the comb. That helps to in the swift movement of the comb. Okay, and the wells are also well formed.
If the gel is to be used immediately, remove the tape from both ends of the tray and continue with the activity. If the gel is to be stored for later use, keep the gel in the gel tray, leaving the tape on, and store it at 4 degrees Celsius in a small plastic bag.
Okay. So that was about, that was about how you cast a gel, agarose gel. And then when the gel is ready, you keep it into the tray and load your sample and put on the power supply. Power supply is important because it will drive the movement of the ionic species. So whatever species are charged, DNA of course is charged, it is ionic, it is negative in charge in the medium, it will allow the flow of that, okay, due to the voltage that it applies. Now, yes, we move on to the, so when we talk about gel electrophoresis, agarose gel electrophoresis and Polyacrylamide gel electrophoresis are the two types. If I have not written here. If we go back to our main slide here, if you see, we have now done Agarose gel electrophoresis and we are moving to polyacrylamide gel electrophoresis. Agarose and polyacrylamide gel electrophoresis have certain differences when you're going to use them. The first major difference is Agarose is used for separation of nucleic acids, DNA and RNA samples. Okay, when you talk about protein, then you're going to use polyacrylamide gel electrophoresis. The other one of the other differences is that Agarose gel electrophoresis is usually horizontal. If you see, it is horizontal, and protein gel electrophoresis is vertical. Okay, we are also going to see how it works, how to cast a gel in the laboratory, how to cast a protein gel in the laboratory. We are going to even see that. Now let us move to because I don't have a slide on that. Maybe I will include one slide here. So when I talk about gel electrophoresis, Agarose, and then you have here as PAGE, or you can also call it as polyacrylamide gel electrophoresis, the long form. Okay, Agarose is large pore size, because you also observe that it is only the Agarose powder and the buffer that you're going to use. There are no other components there. It is just one single component, that is the Agarose. It is used for DNA and RNA separation. Okay. You can also, when you see the bands, no, these bands, when you see, for suppose this is the band that I am interested in, this particular band. Now what can I do if I want to work with this? Now this is a pure band. Look at this, the shape, the clarity is so good. It is a pure sample now. So what I can do is I can use a small blade and I can cut this part from the gel, this part, and there are certain kits available where you can extract your DNA from this piece of gel, and then you can use that DNA for further experiments. Okay, so it is that pure. So here you can do the same for DNA, RNA. You can check the purity, you can check the quality of it, and you can use that sample. You can extract your DNA, RNA sample from the gel using certain kits, okay, certain molecular biology kits. You have polyacrylamide gel. This is used for separation of protein, okay, or small sized DNA, not large, small sized DNA. Okay. Now the gels are actually this. If you see, the Agarose gel is usually made in TAE buffer. Okay, it's a tris acetate EDTA buffer. So tris, this part of the buffer is, tris is a base. Okay, tris is a base. Acetate is a weak acid. So it is a weak acid, weak base buffer. Okay. E stands for EDTA. EDTA is a chelating agent. So EDTA has affinity to bind to metals. Okay. So what happens is, if the sample, magnesium, for example, magnesium is known to chelate, bind with the DNA and harm the structure of the DNA. It may disrupt the structure of the DNA. So we do not want magnesium to run in our sample. So what do? We make the gel in the TAE buffer, and the EDTA takes care of the magnesium. So any free magnesium, if it is there, then the EDTA will bind with that magnesium, okay? And that magnesium is not available now to go and harm our DNA or harm the sample. And then this magnesium is taken care of, okay? So DNA is going to be intact. It is going to be pure because EDTA has already bound it to the magnesium, because DNA is chelating agent. Chelating agent are agents which have affinity towards metals. So this basically is a buffer which is neutral in pH. So your Agarose gel is neutral. The pH is neutral of the Agarose gel because it has been made in a buffer which is also neutral. Okay. Now, when we talk about polyacrylamide gel, here you are going to separate the proteins. So here it was basically size. Why? Because when you talk about DNA, RNA, we know nucleic acids negatively charged. So that charge is common for all of them. So only size is a varying thing. But when we talk about proteins, in a mixture of proteins, we don't know, there can be plus and minus proteins, like positive and negative protein, negatively charged proteins. So it will be, the separation is based on molecular weight. Okay. Then you can also say crudely that it is also based on the shape of the molecule. Okay, shape, size of the molecule. Charge is another aspect that is also considered here. Okay. Now, when you talk about gel electrophoresis, it is Agarose gel electrophoresis, and then it is polyacrylamide gel electrophoresis. Now, when we talk about polyacrylamide gel electrophoresis, there are still two types. One is native and one is SDS or denaturing gel, that we will see now. So, basic principle of polyacrylamide gel is separation of your biomolecule or of the protein based on the charge on the molecule. So the charged molecules are separated based on their electrical charge and size within the matrix. Just like how I explained to you that the starch slab is made. Similarly, here also polyacrylamide will be a gel-like a thing. It is going to be a gel, but in a form of a film. Okay, in a form of a film which is not very thin, thick. So here, if you have a mixture of charged molecules, some of them are going to be positive, some of them are going to be negative. So if you separate them, you'll see that the blue ones are the positive molecules and the red ones are the negative molecules. Now this blue one, again, even if all of them are positive, look at their size. Their sizes are of different types. So this is one, and this is one. So they all come together, they all are positive. So you first separate on the basis of size, charge, then the basis of size, and then finally you are going to analyze, you're going to identify, and you're going to purify. Okay, so that is the approach when you do electrophoresis. Polyacrylamide gel electrophoresis, P stands for poly, A for acrylamide, G for gel, and E for electrophoresis. Then I said that there are two types, native and SDS. So what does the word native means? The word native is actually original, or it is unmodified. So whatever analyte you are going to run, whatever sample you are going to run, and that specific analyte which you want to separate, you want to study, you want to purify, will always be in its original form, will always be in its unmodified form. You're not going to alter the protein, the analyte, the biomolecule, you're not going to alter it. Okay. But when you talk about SDS-PAGE, SDS-PAGE is going to alter, it is going to modify the protein structure. So how is the protein structure? Is it straight or is it folded? Is it straight as a ribbon or is it folded? How is the protein structure? How is the protein structure? Are you able to hear me, everybody? Or I'm not so audible? Okay. Folded. Anybody else? Only Diksha has understood that it is folded.
Folded.
Folded. Okay. So it is folded. Okay. And when I say that you're going to alter, then it means that it is folded. This is the native state, and you are going to straighten it. That is the modification. And this modification is done by SDS. What is SDS? SDS is a detergent surfactant sodium dodecyl sulfate. Okay, so when the protein comes in contact with SDS, it alters, it breaks. Okay, it breaks and it linearizes. So the SDS will break all the interactions. We saw na ki protein amino acids are going to interact, and they fold in that manner. So all these interactions that are there between the amino acids, SDS is going to break them. So all the bonds which are there, which are giving a protein a particular fold or a particular structure, 3D structure, those bonds are going to break. The interactions are going to break because of SDS, and hence the protein is going to linearize. Along with linearization, SDS is also known to impart a charge on it. And what is the charge? Negative charge. Now the protein after treatment with SDS is not only going to become linearized, but it will also have a negative charge. Okay. So it will basically, it's going to nullify. It is basically going to nullify. Now, since the charge is not an issue, because all of them are going to have the same sort of charge, so now this separation is only based on molecular weight. Okay, we know proteins have charge, plus and minus, but SDS-PAGE is that kind of electrophoresis where we nullify the charge. Now we bring all of them at the same charge, but we are now exploiting the property of molecular weight. So we are going to separate those proteins, the mix of proteins based on their molecular weight. Whereas in native, you are not going to disturb the configuration of the conformation of the protein. You are going to keep it original. You are going to keep it native. So that's why the separation is going to be based on charge, size, mass, whatever you want to call, shape. All of these factors are important here. Okay, because here what is your the folded protein is going to be like this, and because there are all different kinds of amino acids, it could be having plus plus. Wherever there are amino acids with positive charge, there is going to be a plus charge, and wherever there is amino acid which is negatively charged, so it could be both. So this protein now is in the native form, can be positive, can be negative. It will have its own net charge, Okay, you're not adding anything like SDS to this and changing the charge, or you're not adding SDS or nullifying the charge. You're not doing that. This will come with its own net charge. Okay, it could be slightly positive, slightly negative, depending upon the amino acids. If majority of amino acids are positive, and only a couple of few amino acids are negative, so the protein will carry large positive charges but less negative charges, and vice versa. Okay, so this method is important also because it helps us to know the protein behavior. Okay, so if you run a gel repeatedly, if the sample that you have and you keep on repeatedly running the gel, and you see that the same protein is you're able to see the band of the protein at the same position, so you can comment upon the behavior of this protein under these certain conditions, because you have done or you have repeated the procedure for more than 4 times, more than 5 times. Okay, so repeated analysis can tell you, repeated experiments can tell you a lot about the behavior of the protein. Okay, now in the case of SDS-PAGE, suppose now you have a gel, and okay, you have a gel and now you have loaded the protein mix. Okay, all the 3 protein molecules, this is one protein molecule, This is the other, and this is the other. Now, three of them are carrying the same, after the SDS treatment, the charge on them is the same. Okay. Now, what is the difference that you see on these protein? Charge is same. So what is the difference? What is the difference on all three or in all three? What is the difference?
Size.
Yes, correct. So when the size is different, the mass will also be different. Right? Okay. Then now I have
Yes,
applied,
ma'am.
yeah, I have applied the electric field here. Okay, so this is one electrode. And this is the other electrode. So red one is the anode and the black one is the cathode. Okay, and then I connect it to the battery. I connect it to the power pack. So here I'll connect it to a power pack. Now when I apply, all of these three protein molecules will have different size shape. The charge is, say, same. Okay, the charge is the same after the SDS treatment is done. The charge is going to be the same. So now the protein will be separated based on only their molecular weight. Okay, so we saw that the smaller proteins, the smaller ones, they will travel faster. They will travel faster. This will take some time to go ahead because it is large. Okay. Now, if I do a native gel, it means that they could be of various charges as well as different masses also. So based on that, then the separation happens. So if this protein is negatively charged, this will move towards the positive. If this protein is negative charge, sorry, this protein is positive charge, then it is not going to move faster because this is positive, like charges repel each other. So the migration of this protein will be, the rate of migration of this protein will be different as compared to this. Okay, so based on the charge and based on the molecular weight and the size and the shape, a lot of separation, purification is determined or actually decided. Okay, is this clear so far?
Yes, ma'am.
All of you?
Yes, ma'am.
Okay, so polyacrylamide gel electrophoresis. Now the gel unit looks something like this. I have some videos also. We are going to see how to cast and all of that, how to make the gel, what are the different components here. So when you talk about polyacrylamide gel, this is how it looks internally. Okay, when you look at it, it is just a very thin, nice jelly slab, but internally the structure, the mesh network is like this. And when you load the protein mixture, you can see in this particular figure, there are some biomolecules which are green, some are yellow, which are golden. So it's a mixture of proteins. Okay, now based on the pore size, so these are this cross-linking or this networking gives a particular pore size. Based on the pore size, the migration will also affect. And then you will look at it like after you load the sample and after you apply the electric field. Okay, after you apply the electric field, the molecules have migrated. The larger ones are retained here, the medium ones are in the middle, and the smaller ones made it first. Okay, so the size is one of the important factors. Now when you talk about agarose and polyacrylamide gels, so polyacrylamide again is of two types, native and SDS. Okay, what are the other reasons why you go for SDS and all that? We will also discuss that. Agarose gel is horizontal, polyacrylamide gel is vertical. Bigger gaps, so the large pore size, small pore size. Okay, better for large molecules, better for small molecules. Okay, and mostly DNA, nucleic acid samples. So here either small DNA or proteins. So that is these are the differences between agarose and polyacrylamide gel. Now when you cast a protein gel, you when you make this polyacrylamide gel, there is acrylamide. Okay, now this acrylamide, so these are the components of the casting of gel. And then there is bisacrylamide. acrylamide, then there is bisacrylamide. And when you mix acrylamide, bisacrylamide, and there are some other components like APS, timid. Okay, these are some important components. Of course, buffer is there. All of this is prepared in the buffer only. You can't prepare any of this into any other solvent, even not water. It has to be in the buffer, and that water that you are going to use has to be distilled, double distilled water, extra pure. Okay, there has to be no interference of any impurity in that through that water, because whatever you are going to run, the sample that you are going to run, you have to check the purity of it. But your medium itself is impure, then how could you comment on the purity of the sample? So everything has to be done in very pure conditions. When, see this, basically these are the two components, they cross-link. And because of the cross-linking, like this, because of that, the mesh network is formed. And because of this, you will get pore sizes. Okay. So we will also see how it is prepared. So acrylamide is there, bisacrylamide is there, APS is there, ammonium persulfate is there, timid is there. All of these are the components of the polyacrylamide gel. If you're doing a native gel, then yes, these. Okay. If you're going to do an SDS-PAGE, then one more additional compound is going to be, which is SDS. Okay, this is also known as a denaturant detergent. Why denaturant? Because it is distorting, it is breaking, it is denaturing the protein, the 3D protein. Okay, now if a mixture is given to you, and in that mixture, see, you must have studied about isotopes and isobars. So in the proteins also, when you study enzymes, there are isoenzymes. Now these, and every protein or every protein may have subunits. Okay, so those subunits cannot be seen when you do a native gel. So there can be a monomer, there can be a dimer protein, there can be a trimer protein. Okay, so there can be different subunits of a particular protein. Now they will all have different molecular mass. Okay, so when you do an SDS gel, when you do a denaturing gel, these different subunits also will get separated, and you will see that how much does each subunit weigh, or what is the molecular mass of each subunit, how much kilodaltons is it. That is not possible in the native gel. It is only possible in the denaturing gel, or it is also called as SDS gel. So that is why we go for SDS if you're working with, say, an isomeric protein. If that particular protein has 2-3 subunits, it is not a mono unit, it is not a monomer. If it is a monomer, then you always go for native. But if you're working with a protein which has different subunits to it, then you need to identify the molecular weights of all of those, and then that is only possible because of SDS gel. Why? Because you're nullifying the charge. So when you're nullifying the charge, only thing that is going to determine the gel run is the mass or the weight of the proteins. Okay, so now when you're preparing the gel, no, there are certain steps. So this this gel is vertical. First of all, it's vertical. Okay. Now this part, which is dark green color, is called as separating gel. The upper part, which is light green color, is the stacking gel. What is the difference? The components are going to be the same. The ingredients are going to be the same. Acrylamide is in large proportion. Bisacrylamide is in a little smaller proportion. Timid is also very small. You know, timid is very small. APS also that is used is also very, very small. Only 10%. You have to first make 10% APS, out of which you have to add a little amount to the gel. Now, separating, stacking, all these basic ingredients are going to be the same, but what is going to be separate is the proportion. Okay, so the proportion will change the pore size. So this area is your loading area. Here is where you're going to load the sample. You remove the comb, you will see the formation of the wells. you're going to put the sample in the wells. Okay, so this is how the comb is inserted. After the inserting of the comb, you will see that these wells are formed. You're going to add your sample to the well. So this loading of sample happens in the stacking gel. Then you apply the electric field. When you apply the electric field, they will all start migrating. You will see that the gel front is like this, because again the dye that is used here is also blue in color. So that dye will give you the you can track the run of the samples, okay, the migration of the sample. And after the gel is run, you remove the gel, you then start the staining procedure. So that is how you will get you will see the bands. Otherwise, after just running the gel, you will not be able to see any bands. You will have to develop. It is something like the old age cameras, the cameras which used to come with the roll. You click pictures, but you had to give it for developing. After developing only, you could get the prints. So developing is a procedure. There are certain chemicals that are used. Fixation is one of the processes, washing and all that, and then staining. And that's how you see the bands, okay? So here again, same thing, you mix the ingredients, then you pour it. After you pour the separate, so if the gel, this is the size, then from here till here only you have to pour your separating gel, only till this level. After the separating gel solidifies, then you add the stacking gel. After you add the stacking gel, you insert the comb, then you remove the comb once the solidification has happened. After you remove the comb, you will see the formation of the gel. So now we'll see a video where the preparation of polyacrylamide gel is shown.
What science says about procrastination?
Gel. Here is the apparatus for casting the gel. There are 4 different parts to this gel apparatus. First of all, you have 2 glass plates. You have a short plate, and then you have a tall plate.
Yes, so there are 2 plates that are required, and in between the 2 glass plates, okay, you are going to pour the mix that you're going to make. So the glass plates have to be clean. Again, if you see, you are going to wear hand gloves. Everything has to be done in a protocol. Follow the protocol, because the reagents that you're going to use, the ingredients, acrylamide, bisacrylamide, temid, APS, they are neurotoxins. Okay, they are not green chemicals. They are going to harm. So that's why you have to protect your skin and not touch also, because it will the fingerprints will also come on the glasses. So while handling the gel, always make sure the gloves are worn.
Then you also have a casting frame and a casting stand. What you do here right now is you want to place the short plate in front of the tall plate like that, and then put it into.
So one of the plate is short, one of the plate is tall. Depends upon which company electrophoresis unit you are using. There could be a slight variation. So this is a Biorad company electrophoresis unit. So some alterations are there. Somewhere there is both the glass slabs are actually of the same dimensions. There is no difference. Here there is a slight difference.
The casting frame. After you put in the casting frame, you secure it.
Yes, so then when you insert both of them inside the casting frame, you're going to lock it from both the sides. Again, that locking is important, because otherwise, if there are gaps, then whatever you're going to pour is going to come out of the mold. Okay.
Clamping it, and then you want to check that the bottom is flat. When everything is done, then you can put it on the casting stand. Okay, after we have assembled the gel apparatus, what we need to do right now is we will take the comb and we'll place it in between the glass.
So this is a highly advanced electrophoresis unit, I will say, because you don't have to really worry. Once you have done the locking properly, there will be no leaks. You have to make sure that at this bottom also there is no leak. Nothing is coming out from both the sides also. Because when you're going to pour the mix, when it is liquid, before just it starts gelatinizing, before it starts cross-linking, it is free flowing. So if there is a leak here, if there is a gap here, if you have not locked it properly, everything will come out of it.
Cross plates like that. And we'll take a marker and we'll make a mark approximately 1 centimeter below the cone right there. We'll take the comb
So
up.
he has marked it here depending upon the length of the combs. So the teeth of the combs. So till this till below the black mark, till below. Okay. So this arrow here, this is going to be the separating gel area. And above the black mark is going to be the stacking gel area.
Well, what we want to do right now is we want to add a little bit of water to the glass plate to see whether they're leaky or not. So
Yes, so he has added a little bit of water to it through the pipette. So just to check that it is not coming out. So if you add water and if it does not leak, it means you are good to go. Now you can pour your gel mix.
So you can see right now, the apparatus is not leaky. So therefore, we'll draw out the water using a piece of filter paper.
You cannot leave the water inside, the water that you have used for testing whether there is a leak or not. You have to remove that water. So how do you remove the water? Now you do not disturb the gel unit. If you disturb the gel unit now, there can be a leak. Now that you have assured that there is no leak, keep it as it is. Instead of tilting and removing the water, or instead of picking up the unit and doing it upside down, instead of that, the best way is to take a filter paper and dab all the water out.
Okay, now we'll be casting the resolving gel.
Yeah, so separating gel is also known as resolving gel because that is the place where the proteins are going to get separated or they are going to get resolved. So here you are going to use acrylamide, SDS is used, ammonium persulfate is used, temid is used, okay?
So I have added everything on the recipe except for timid. Timid is going to initialize the polymerization reaction. So
Yes.
after you add it,
So temid actually, as I said, the polymerization, the cross-linking reaction happens between acrylamide, bisacrylamide. So this polymerization is initiated by temid. So never add temid first. If you add temid first, it will immediately start polymerization and everything will become solid in the flask itself. Before even you pour it into the mold, it will start getting solidified. So temid has to go last.
timid, you should cast the gel right away. So now I have just added teammate to my solution. So we want to pour the gel right away. We want to pour the gel till the gel is at the same level as the mark. It's okay if you introduce any air bubbles right now. We'll fix that later. So with the gel,
Well, he says it is okay if you add any air bubble right now, but I would say avoid adding air bubble to it. And when you are adding the mixture to the slabs, make sure that you swiftly, so the motion should be so swift that there should be no air bubble coming into it.
go to the mark. And then we'll remove the bubbles by adding a layer of isopropanol on top of the gel, like that.
So isopropanol, if you add isopropanol is not going to mix into your gel mix because your gel mix is water based. Isopropanol is a solvent, so it will not actually interfere there and it will stay on the top itself. It will also make sure that the level of your resolving gel is not abrupt. It is a uniform level, okay?
So after the resolving gel has polymerized, we will try out the isopropanol using the filter paper again.
At this point of time, if you want to pour it off, you can lift your gel unit and you can pour it off also. Why? Because now you're not going to disturb the you're not going to introduce any leaks because the gel has already polymerized here and you have everything is properly sealed now. You can also turn it down or you can absorb the isopropanol like this. Don't keep the isopropanol and then add the stacking gel. Now there will be no space for the stacking gel if you don't remove the isopropanol. So first remove the isopropanol and then add the stacking gel mixture.
After we draw the isopropanol, we can cast the
So
stacking
you
gel.
will see that the ingredients are the same for separation and the stacking gel. Okay, but only the proportion varies for both of them. So if you see in the resolving gel or in the separation gel, the pH was 8.8. Here in the stacking gel, the pH is 6.8. So that is the difference. And if you're doing an SDS gel, of course, you're going to add SDS. But if you're going to do a native gel, you don't need to add SDS to it. Okay. Here also timid is going to be the last. As soon as you add timid, give a gentle stir to the mix and then add it to the mold.
Right now I'm going to add cement to the stacking gel. So we'll fill up the rest of the plate with stacking gel. Fill it all the way to the top. Like that. Right now you don't want to introduce any air bubble because you're just going to get trapped. And we'll put in the cone. And that's how you cast an SDS-PAGE gel.
So after it solidifies, all you have to do is you have to just lift your comb. And when you lift the comb, you will get nicely well-formed wells. Okay. And in those wells, you're going to load your sample. Now you load the sample and you run the gel. You apply the electric field, you run the gel. You will have a dye front because you have added a blue color dye to your sample. So you will know till where it has come. You don't want to overrun the gel also. Then what will you do? You will remove. Okay, you'll remove the gel. After removing the gel, the most important thing is
I defeated diabetes.
the most important thing is to stain it, because if you don't stain it, you will not be able to see where are the protein bands. So if you look at this unit now, this unit is having a cover. The cover is important because otherwise any other contaminant from that outer side can fall into it. Secondly, you want to minimize the rate of evaporation because you are applying electric field, the temperature rises, so there can be evaporation of the buffer. If the evaporation of buffer happens, your gel can go dry. So you have to make sure that the gel is never dry. So sometimes you might have to also top up some buffer. Okay. So this is the unit, and there is when your gel is ready, when you load the gel, before loading the gel, buffer is added. Don't load the gel and then add the buffer, because the buffer will rush into the well and all the sample that you have loaded will come out.
Today, I'm going to show you how to disassemble and stain your SDS-PAGE gel using either Page Blue, Comasi, or silver staining. After you have unplugged your electrode, remove the lid. Take out the inside chamber and carefully pour the buffer.
These type of units, you can run 2 gels on both the side. Okay, just like a sandwich. If you imagine a sandwich, there is bread on one side, there is bread on the other side, and in between you have your filling of the sandwich. So the 2 breads are the two gels you can imagine. Okay, so here on one side there is one gel, on the other side other gel. So because when you're working in a laboratory, there could be many people working, and there is say 1 unit or only 2 electrophoresis unit to share, then people try to run, 2 people collaborate and they try to run the gel on the same day. Or if you or yourself have so many samples to run, then you can make 2 gels and you can run them all at the same time.
You want to remove your glass plates carefully because they're very fragile and can break easily. Today, I'm going to show you how to stain your gel using Page Blue. Take a microwavable container, fill it halfway with distilled water. you want to rinse your glass plates because water helps to lubricate the plates and make them easier to
Yes,
stop.
so you need to first wash the plate. After the gel run is over, wash the plate because water will ease out the removal of glasses. So it acts as a lubricant. And then you use this particular piece of plastic that has been provided, and you can just nick out the plate.
You can remove the stacking gel from here. It's up to you, but I always remove my stacking gel. But when you remove the stacking gel, make sure you do it carefully not to rip the resolving gel. Put the plates upside down. Hopefully the water will get between the gel and the plate. Therefore, the gel will come right off your plate and into the container.
So you have to first take a tray which contains double distilled water, and then you remove the top glass slab, and then you can invert the gel, which is now stuck to the other piece of the glass. Just invert it into the water. The water will get in between the gel and the glass, and it might come off easily. Sometimes it may not come. Then you might have to use your skill, use something very very thin and slide it just between the glass and the gel, and then try to remove it.
If it doesn't, you can lift the corner of your gel a little bit, and then the water will get between the gel and the plate. So you want to wash your gel a few times with distilled water. Make sure you put the water in gently so it doesn't break the gel. When you pour the water onto your gel with your finger so it doesn't come out and break into the sink. And before you microwave, we want to fill out the container with water. And we'll microwave it for about a minute. And we'll let it shake on the shaker for 5 minutes.
So not all staining procedures include microwaving. There are certain staining procedures that will ask you to microwave the gel before you start staining it. So Page Blue is a dye, a staining dye, which is again commercially available.
Before we transfer the gel, we want to make sure we remove excess water because we would not want to dilute the dye. And then we'll microwave this for about 30 seconds. By heating it up again, this helps the dye to be absorbed into the gel.
Yeah, so heating is a procedure which will only increase the absorption of the dye in the gel.
That is, shake on the shaker for about 10 minutes. You can shake it longer if your dye is not as fresh. And after the 10 minutes, we'll remove the gel from the dye. And again, we want to remove excess dye. We'll wash the gel as we did before by using distilled water. So during the destaining process, you can change your water several times, or you can use the king white trick. Put in 2 pieces of king white. What king white does is that it's going to absorb the excess dye in the solution, which will speed up the destaining process.
So when you remove it from the stain or when you remove it from the dye, you need to again give washes because there is excess of dye, and in that excess of dye, you will not be able to see the bands. Some of the bands may be lighter. So if you need to really clarify, you need to clear off the background of your dye, of your gel. Okay. Now these are some techniques over the years when people work in the lab, they develop some tricks and hacks. So this is like drop the tissue paper inside the water, and so that the excess of dye can be absorbed by the tissue paper so that you get a very clear gel and only the blue bands will be seen. So this Page Blue stain, you have to stain it for 10 to 20 minutes. You can reuse it also. So today, if you have used a fresh stain, you can stain the gels like 2-3 gels. You can keep it. You can repeatedly use it for the next time also. Make sure you're not using for too many repeats. 1 or 2 repeats is okay. Then you can discard the gel because the efficiency goes down. In a fresh stain, the gel will be stained say in 10-20 minutes, but in a reuse stain, it will take a longer time. Then you have to de-stain also. Remove the excess of stain. You can use water, give 2-3 washes of water, keep it in water for some time, keep it on the rotator.
So that's how you stain your gel using page blue. Now I'm going to tell you how to stain your gel using Comasi. First of all, you take your gel, you put it directly into your Comasi stain. The staining
So
time.
Comasi is an older method. During my PhD, we would make the stain in the lab itself. Comasi blue stain was made in the lab. So we used to do a bulk preparation, and many of us would take turns in making it, and then we used to use it and reuse it also. So it's an older method. Page blue is a comparatively new, and it's a commercialized. So the preparation of Comasi blue in the lab also may vary from person to person, because if I'm making, there can be manual errors in the weighing down. If any other person is making, he or she will also have some errors done. So that used to never be uniform, the making of Comasi blue. But page blue again is a commercial, so it is made in a company. They make sure that all the ingredients, all the weighs, all the weighing and everything has no error. So
it's about 20 to 60 minutes. And after the staining is done,
and also you note the time. So Comasi blue takes about 20 to 60 minutes, whereas page blue is only taking 10 to 20 minutes. So it means that the time is a very important factor. So if you're doing, say, a gel, you start a gel in the morning, you stain, and in 10-15 minutes itself you get the results. You can plan the next experiment very quickly based on what you have seen just now.
Gel and transfer it into a destaining solution, which is made out of methanol and acetic acid. For this protocol, you do not need to microwave.
So here you are going to not use water for destaining, but you're going to use methanol and acetic acid solution. Again, methanol and acetic acid, these are the solvents, this is acid. Again, you will have to input a lot of money. Also, the smell of acetic acid is so bad, it causes headache. So you are eliminating this step when you are using page blue. Using of solvent. So when you use a solvent, you just can't throw it in the sink. When you throw it in the sink, that gets mixed, and it is dangerous for the environment. So again, it's not good for the environment. So when you are using page blue, you are eliminating this step. So it is more greener. Okay, it's green chemistry.
But it does take a little bit longer compared to page blue. If you have thin bands, then you want to use a more sensitive staining protocol, which is silver staining. This protocol involves.
Now, when you're using Comasi blue will only stain proteins which are in higher concentration. So you will be visibly seeing thick bands of blue color. Okay, that's because the thicker the band, the concentration is more of the protein. Okay, but there are certain proteins in your sample which may not be in a higher concentration. They may be in a lower concentration. So Comasi blue will not help you. Page blue will also not help you. Then there is silver staining method, which will help you because it is a more sensitive method. You can get faintest bands, but still you can see it on silver staining because it's a highly sensitive method.
Here's the steps. First of all, you need to fix your gel in a methanol acetic
so
acid solution.
the basic running of the gel is the same. You cast the gel, you run the gel, you remove the gel, wash it into water. Now what you'll do is you're going to fix the gel. So the treatment is different. Fixing of gel, here you're going to use methanol acetic acid solution.
Then you oxidize your gel by putting it into an oxidizing solution.
Yes. So you
after this step, you want to wash your gel really well.
So you have to oxidize the gel. There are certain chemicals again that silver stain. So there is silver component, and there are other components which you're going to add, and you're going to oxidize your gel. Then you're going to give water washes to remove the excess of the oxidizing agent there.
Several times with water. Then you can stain it with silver nitrate.
Yeah. So then you have silver nitrate stain that is going to be the stain actually for 20 minutes.
Quickly rinse excess silver nitrate off with water. And when you want to develop your gel and try to visualize the band.
Yes. So development is sodium carbonate formaldehyde solution. This also is a very bad spelling developer, but silver staining is very sensitive. So you get the faintest bands also you can see properly in your mixture.
Put it into a developing solution. You don't want to develop it for too long. So when you want to stop the developing process, you put your gel into an acetic acid solution. Again, this process does not require using a microwave. You are going to use hazardous materials. It does take a lot longer, but overall, you have a more sensitive result. Those are 3 different ways you can stay sensitive, but beware of the hazardous materials that you will use.
Yeah. So I want to show you how the silver staining gel looks. Okay, so can you see this gel on the screen right now? All of you? Can you see these gels here? Okay, so this is how a silver staining looks. Okay, look at the clarity. Look at this gel especially. So if you look at this, can I magnify? You'll see that the gel is almost clean. The background is almost clean, and you can only see brown bands. Okay, even the faintest, the tiniest bands are also being seen very properly. This is how silver staining is effective. Now this one is a Kumasi blue staining. Okay, this particular blue one. So Kumasi blue staining, silver stain protein. So both samples have been there are. So what has been done is actually the same samples have been loaded. They have been cut, and both of them have been stained by two different procedures. So one is Kumasi blue, one is the silver stain. So look at the sensitivity of the silver stain procedure. Okay, which some of the bands like this band, this band, this band is seen here in the silver stain, but here it is not very clearly seen. So that is why silver stain is supposed to be a very sensitive method. So when you develop a gel, when you stain a gel with Kumasi blue, it looks like this. All the bands appear blue in color. So the darker the band, it means the concentration of your protein is higher. The lighter the band, the concentration of the protein is lower. Okay, any doubts in this electrophoresis? Yes, students? Any doubts, students? Waiting for a yes, no? Okay, great. So we